So continuing this question further, yesterday we did till the B part, right? And then C part was not done. So C part, actually there is a very simple way to do it without thinking about the complicated equation that we have.
Hmm.
So there is a complicated equation. Where is it? Shunt excited motors. One moment. Yes. This equation is, I believe it doesn't work, or there is some conversion factor missing or something for generators. So for
Hmm.
generator, especially in this case, it's very straightforward with how to do it.
Hmm.
We will go through the efficiency side or the mechanical side.
Okay.
Okay, so scroll
Yeah,
down
the
further.
efficiency.
So C part. So we know that UI equals 433 volts
Hmm.
and the current is 100 amps or 110. How much was it? 100 amps. 100 amps is being delivered.
Yes.
So like we saw with motors in this case as well, what we will see is that the power input, which is mechanical, is equal to UI times I,
Power mechanical.
and that is equal to torque input times 2 pi n. In the case of the DC motor, like this is we are looking at the case of a generator, but in the case of a motor, it's slightly different. Um, Here is the UI, P mech, there is the I, and this is UT. P mech is just UI times I, and P electrical is UT times I. Here the situation is reversed. It's not
Hmm.
reversed actually, the equations are still the same. It's just that in this case UT greater than UI, and in this case UI greater than UT. That's all. The equations are still the same. So I just continue with that. Torque input equals UI times I divided by 2 pi n, which is 433 volts with 100 amps divided by 2 pi times 1050 divided by 60. Solving this will actually give you 396 or 397, something like that.
Okay.
So sorry, 393.8. 393.8 Newton meters, which is exactly what is given in the as the answer. 79 is what we
Just
get.
one question.
Yeah.
My question is for the motor,
Hmm.
the P input is electrical, right?
Yes.
And P output is P mechanical
Correct.
for motor.
Yes.
Okay. I'll just write this down, please. So for
I
motor.
mean, it's straightforward, right? For motor, it's you're converting electricity into mechanical power. Generator is the other way around.
Like, just wanted to know, like, how does the generator work? I haven't studied it.
No, it's the exact same. Construction is exactly the same thing. It's just that
Mhm.
if and the field coils are still energized with a battery, like we saw here. You still need a field voltage to energize the coil, but that's all. It's not actually giving any power. Can you hear me?
Yeah, yeah, I can hear
Okay,
you.
okay. So that it's not consuming any power. It's just delivering current, but there is a
Mhm.
voltage. So there is a field generated in the stator coils. The rotor is spinning. So there is
Mhm.
a change in magnetic field that it is being felt there. So voltage is induced there, and that voltage gives us the power supply.
Okay. Okay.
Yeah.
Okay. So, hmm. Uh, and one thing more, have you sent me these, like your notes, like this one, the one showing on the screen?
Yeah, yeah. I mean, I sent till yesterday's part, and today's part I will send after it's done.
Okay. Okay.
Yes.
Okay. Okay.
Okay. So let us
Hmm.
continue.
Hmm.
So that was this question. So this is
Hmm.
a similar kind of question, little bit harder. You can try.
Okay, I'll try it right now.
No, you can do later.
Okay. Okay.
So moving on to wound field excited motors.
Hmm.
Here the difference is that the if you noticed, sorry. So the difference is that the field is in series. It's not parallel. That's why it's called series field. So earlier in the shunt excited motor, it was in parallel. Like the field coil was in parallel with the armature. Here it's in series. That means
Hmm.
earlier we had for for shunt V coil, V stator equals V armature, but the currents are different. I shunt is much less than I armature, but here it's the other way around. V coil is much smaller than V armature in general, like at least at nominal operation, and I shunt, or like the field coil is equal to I armature. So because of this, it becomes a bit more complicated to handle this motor, because here you can't. It's not so easy to control it. You need to control current and not voltage. Current is harder to control in general than controlling voltage, and the speed control is also not so good. But
Hmm.
since the field current is so large and not like the shunt excited motor, we have very good starting torque. It's a very high current flowing in the beginning, so the starting torque is good. So we have some equations. Let us also look at the equivalent circuit diagram. So this is the field coil, stator. As usual, we have the armature resistance
Hmm.
and we have the induced voltage. Once all this and all this combined is the total voltage.
Hmm.
We can ignore the voltage drop across the stator field, it's negligible.
Hmm. Okay.
So very similar to last time, we will solve with like armature voltage drop and to get the induced voltage and so on. One important difference to note here, look at how
Hmm.
the UI is related to RPM. There is no like earlier we had K1 phi n, that was okay
Hmm.
because this phi is a constant. But here the
Hmm.
stator field current is changing, which means the field strength is changing. So we have the I term here in the induced voltage,
Hmm.
and for torque as well, because this field is also changing, like this field strength is changing and the current flowing is changing, so you have I square instead of I. So torque is proportional to I square here.
Okay.
Okay. N is the
Hmm.
N is different equation this time because the properties are different, and this is a
Hmm.
modified form, and this U is U total. And usually when a question talks about nominal voltage, they're talking about total voltage. They're always talking about the input, the supply that you're giving to the motor, not internally what's happening. So let us look at
Okay.
the torque versus RPM graph. So as we expected, it's going to be quadratic because look at this equation.
Hmm.
This is perfectly what is being shown on the graph. Next slide. We have torque, and this RPM is in the denominator. That's why it's exponential curve. It's decreasing, exponential
Hmm.
decrease because n is in the denominator.
Hmm.
Again, this is similar to shunt excited motor in the fact that the torque is decreasing with increasing RPM, but you can see it doesn't go to zero. It's going to a very small value, but not zero.
Hmm. Okay.
At least I think it won't. Yeah, it won't. Because you see, there is no negative sign. All the terms are positive. Why will it ever go to zero? As
Hmm.
the speed increases, the torque will become smaller and smaller, but never become zero and never become negative.
Okay.
Okay, and that's why we have this nominal operating point. So now we look at the modifications to the graph because of changes in the properties of the motor. Supply voltage, you can see it's shifting up.
Hmm.
UT square is there, that's why, and nothing else is changing. So it shifts up, like for a higher voltage. Armature resistance shifts down because higher armature resistance means the denominator is larger, so the value decreases. But at higher RPM, this K3N starts dominating, so the RA doesn't matter anymore. So that's why at the later ends they are quite close in the value for different armature resistances. Field
Hmm.
weakening, I think it's about the changes in the current or the K3 value, not sure. Anyways, it's not that important. And saturation basically means like the magnetic field is at the peak and you can't increase it anymore. Like there is a limit beyond which even if you try to increase current further, the torque will not increase because the magnetic field is saturated. But
Okay.
that's too much detail. We will not go into that. So let's look at this example question.
Hmm. Beautiful. Hmm. Okay. So
So the process to
yes.
be followed is very similar to what we did with shunt exciter.
So it's asking for power when the n is changing.
Let me see the question again. Yes, yes. So I mean the logical way to do it would be to find torque and then multiply that with RPM to get power.
Okay.
To calculate torque, you need to use that equation which is giving the torque versus RPM relationship, the left side one. And for that
Yes.
you need the armature resistance and you have to calculate this armature resistance first. Or should I solve this?
Hmm. I think you should.
Okay.
Like, will we use the same formulas as the the previous one?
No, we will not. The equations are different, but the concept is still the same. We will still find armature resistance, then the induced voltage. So, sorry, first induced voltage, then armature resistance based on induced voltage. And once we have that, we basically know everything about the motor. We can do whatever we want.
Okay.
Okay, then.
So
No, equations are different. Why are you going all the way up?
I was just looking at. Okay.
But the UT equals UI plus IR, that's still the same. Because
That's still
Kirchhoff
the
law
same
and
one.
the circuit is very similar. So, should I solve?
Yeah, yeah.
Okay,
But I think I. Okay, you can.
okay. So, lot of details given to us: nominal power, nominal voltage, supply voltage, nominal current being consumed, and the RPM, nominal RPM 1500.
Hmm.
So let's just make a quick experiment. Let's see what is electrical power. P electric is Un times In, because this Un is the Ut.
Hmm.
And if you calculate that, you will get 15.4 kilowatts. 220 volts times 70 amp, 15.4 kilowatt, and you can see that is larger than 14.6,
Hmm.
which is greater
So
than
basically, PN is P
so
nominal is
mechanical power.
power output. Yeah.
Yes,
Hmm.
and we also know something, and this P mechanical is equal to U induced times current, and the current is the same.
Hmm.
So we know the current, so let's find U induced. UI equals P nominal divided by I nominal, which is 14.6 into 10 power 3 watts divided by 70 amps. Solving that gives us 209 volts. And as
Hmm.
always, Ut greater than Ui because motor.
Hmm.
Like during the exam, you can make these checks to ensure you're doing it correct. Like motor, you know Ut should be greater than Ui. So somehow, if you make Ui as 230 volt or something, then you know there is a mistake somewhere. You can fix it.
Hmm.
Okay, now we have Ui, we know Ut. So as per the
We can
circuit
calculate
diagram,
K3.
sorry,
We can calculate K3 constant.
yes, K3 as well can be calculated, which we definitely need, and we also need the armature resistance.
Hmm.
So Ui
Okay.
is K3IN. K3 equals Ui divided by IN. So 209 volt divided by 70 amps times. Uh, so I've looked at my calculations. The N is taken in radians per second.
Okay.
So 1500 into 2 pi divide 60. So let's do that. 209 times 60 divided by 70, 1500.
157.08.
No,
No?
0.019.
You said 1500 multiplied by 2 pi
Look at the
divided by.
equation. It's the same one.
No, no, I was talking about the RPM.
Oh, RPM.
Yeah.
RPM is 1500 is given. 1500 into 2 pi
Never
divide
mind,
60.
never mind. I was just telling you the value. Sorry. Yeah,
Yeah,
yeah.
but it's
Okay.
0.019.
Yeah. Okay.
0.019 ohm second, because this unit is radians per second, and radian we can ignore like I said before. So volt by amp is ohm from Ohm's law. So that's why
Hmm.
ohm, and then 1 by second in the denominator becomes second in the numerator. So that's K3. We also need the RA value. So UT equals UI plus IRA. RA equals UT minus UI divided by I, which is 220 volts minus 209 volt divided by 70 amps. This value is 0.157 ohm. So you can
0.1.
note that these values are quite small, like 1 ohm kind of resistance is small relatively,
Hmm.
and this is
Hmm.
even smaller than that because it's basically coils are long conductors, so you are expecting that the resistance will be low, and the more current that you are trying to use, the lesser you should try to keep your resistance. That's why we are going to have thicker and thicker wires if the current carried is more, to have good efficiency, because power loss
Hmm.
is I square Ra. Mostly most of the power loss is I square Ra. So if the current is going to be large, if you know the current is going to be large, then efforts will be made to decrease Ra.
Hmm. Because it has a square.
Yes, exactly. So now let us
Okay.
look at the other case
Hmm.
at 1650 rpm.
Hmm.
U nominal, U nominal is the same. Let's find UI. One more thing, we actually don't know the current value. UN is still the same 220 volt. This is
Hmm.
K3 I1 N1. Let us say this is N1 plus I1 RA. So this I1 is unknown, but RA is known. So I will use this equation to get the I1. So I1 equals
Okay.
UN divided by K3N1 plus RA. UN is 1650 multiplied with no into 2 pi divide 60. Sorry, there's voltage on top. What am I doing? 220 volts. K3 is same 0.019 ohm second multiplied with 1650 into 2 pi divide 60 1 by second plus, see, if you look at this, unit is going to be ohms and you're going to add it with resistance in ohms, so it's working correctly. 0.157 ohm. Solving this should give you 64.1 amps. Let me check that quickly. 220 divided by 0.019 times 1650 into 2 pi divide 60 plus 0.157. Okay, I'm getting 63.95, close enough. 63.95 amps. And as we saw here, the torque is proportional to I squared. So you don't have to go to that complicated formula with torque and end relationship. You can just take Ty by T nominal is equal to I1 by I nominal squared. So T1 equals Tn into I1 by I nominal squared.
But
What
we
is,
still need to calculate the torque, right?
do we have the original torque? We don't.
No.
Okay, we should calculate that. You're right. Tn is Pn by 2 pi Nn nominal RPM. So Pn is 14.6 kilowatt. I did not calculate, huh? Okay. 14.6 into 10 power 3 watts divided by this 2 pi is not a conversion factor. It's just 2 pi and this n is still radians
Hmm.
per second. So what is it? 1500 into 2 pi divide 60. Solving for that, you should be getting 92.9 rpm. Sorry, Newton meter. 92.9 Newton meter. So using that value here, 92.9 Newton meters multiplied with I1
I'm
is
not getting this quickly.
63.95 divided by 70 amps, like the unit cancels out, squared. So you can see the torque is lesser as we expected at higher RPM. Then the answer I get is 77.9, but let me check that. 92.9 into 63.95 divided by 70 squared. 77.53.
I'm not getting 92.9 Newton meter.
How much are you getting?
I don't know why it's happening. 14.79. I don't know why.
Let me check once. Okay, sorry. I fell for the trap. I thought this is an electrical equation, so the 2 pi is different. No. This 2 pi is part of the conversion factor. So, yeah, now it should be correct. Because this is just power and torque, nothing complicated here. If we have power RPM, we get torque. There's no 2 pi squared or anything. I should have got that mistake.
Now even.
No, I'm getting 92.95.
Oh,
946.
2 pi. 1500 divided by 60, right? 92.9, yeah.
Yeah. So try to be consistent. Here I am having three significant digits. Here also I will have three significant digits, 77.5 Newton meters. So that's the answer, I guess. And they want the power as well. Yeah, power is just one more step. P is 2 pi T1 P1 times N1. We know everything else, just calculation. If you calculate that, you will get the power 13.46 kilowatts. But the more core part is getting the torque itself. After that, power is straightforward. So let us
Hmm.
proceed. So we have
Yeah,
one
you
more
can.
question. Do you want to try this?
Okay. So I'll just start the video. Can you see?
Yes, yes, I'm able to see. I will solve right here. So we know to solve it here, it's hard to share. Okay, so we know that it's torque, right, on the left side. No, N. N is U divided by root of 2 pi K3 T minus RA by K3, right? Is that correct?
Yes, this equation
Yeah,
is
minus
correct.
RA by K3, correct. So,
Hmm.
and let us look at the, I will draw it. Yeah. So I will take two cases, nominal, and then another case which is some N1 which I don't know. So N nominal plus RA by K3 equals U divided by root 2 pi K3 T, and N1 plus RA by K3 equals U divided by root of 2 pi K3 2T. Equation 1, equation 2. So now what I do, I divide equation 1 by 2,
Hmm.
and that gives Nn plus Ra by K3 divided by N1 plus Ra by K3. The U's are going to cancel, is the same voltage being supplied, and this is in denominator, so it's going to be inverted. Root 2 pi K3 2T divided by root 2 pi K3T, and you can see now the torque is also cancelling. Torque cancels, K3 also cancels, everything cancels basically except the root 2.
Hmm.
What is nominal RPM? Again,
Okay.
it should be in radians per second, so 720 per minute.
Okay.
N
Okay.
nominal is 720 per minute, which is 12 24 pi radians per second. 720 by 60 is 12. Yeah, answer into 2. So that is 75.4 radians per second. Okay, 75.4 1 by second plus RA, what is zero point 0.5 ohm, divided by K3, which is 0.41 ohm second. And you can see the units are matching. Here as well we have 1 by second divided by N1, which is unknown, plus RA by K3 equals root 2. Now I just take it to this side and then I can solve.
Okay.
So I take it to the right side. 75.4 1 by second plus 0.5 by 0.41 1 by second minus root 2 times 0.5 by 0.41 1 by second equals root 2 n1. So n1 equals, then it's just a case of solving this. 75.4 plus 1 minus root 2 times of 0.5 by 0.41. One moment, times 0.5 divided by 0.41. That gives me 74.9 radians. Sorry, 74.9 divided by root 2. 1 by second, which is 53, 52.9 radians per second. 52.9 into 60 divide 2 pi 1 by minute. It is 505.7, which is close enough to the answer of 480. So it was 480, right? 488. I guess due to the approximations I made, it was off. The answer should be correct. So yeah, that's how you're solving. So we just do this division so that a lot of the terms are cancelling out when we just have this one term left over, and then it's straightforward.
Okay.
So let's move on to AC.